and welcome back. So, in the last class we started looking at the laser action. So, in order to do that, what we did, we took two level systems based on atom, and we looked at different optical transitions that are possible. So, we looked at absorption, we looked at spontaneous emission, and then we were discussing about the Planck's law related to black body radiation. We also stated that Einstein was trying to use this two level oscillator system to explain the black body radiation. So, he took n number of such two level oscillators formulating the overall black body, and was trying to go to the same expression, from the same expression as Planck derived. Okay. And we said that at that point of time, considering absorption and spontaneous emission, he was not being able to do that. So, at last in 1917, you have seen this in the second lecture when we were talking about the development of history of laser development. So, in 1917, Albert Einstein, he ultimately proposed something. What did he propose? He said that there must be another radiative channel of decay of the excited atom. So, what he meant? So, he said that if you take a two level system having same energy, and let us take the same population, then Einstein stated in 1917 that there must be, so we had the process of spontaneous emission without any field, and you had the photon emission. And what Einstein said, well, having this spontaneous emission as the only channel for the atom to decay from excited to ground state is not enough. There must be another decay channel such that its rate constant is B21. Okay. So, this is the rate constant for this separate radiative decay channel other than spontaneous emission. So, how do we depict that process? Let us do that. So, earlier we did not consider any radiation field for emission processes. Now, if I consider a presence of a radiation field, so if this radiation has photon energy equal to the gap of this energy levels, then this will trigger the decay of this atom which is at excited energy level to the ground state. So, in this process what will happen? While coming down, this will release a photon. Okay. So, let me use different color. So, this will release a photon which again has the energy of h nu12. So, this photon coming out is due to the jump that we are seeing due to the optical transition of this atom from 2 to 1. Now, what will happen to this photon? That is not going anywhere. In case of absorption, this atom was taking that amount of energy and making this transition, but here this is going and knocking this on off, and this knocking off process is actually giving us energy in form of this photon. So, this exciting photon is coming out undisturbed. So, this will come out as such, and this process of creating a decay of an excited atom to the ground state by using another photon is known as stimulated emission. It is quite easy to understand here. Earlier we did not have any radiation field, now I have a radiation field which is stimulating this decay process, and which is giving rise to a release of a photon, and the initial photon that is causing this stimulated emission is also coming out. So, by giving one photon I am getting two photon out, correct. So, by stimulated emission I can always increase the number of photon, right. So, if I suppose have several molecules here and I give photon for each one and they make a downward transition, so I will need total 1, 2, 3 photon, and this 3 photon each one will come out accompanied by another photon coming due to the stimulated emission. So, altogether I will get 3 plus 3, 6 photons. So, I will see 1, 2, 3, 4, 5, 6 photons. So, altogether total 4 atoms making a downward transition. My input is total 4 photons and the output is total 6 plus 2, 8 photons. So, you can see stimulated photon will increase the number of photons that will come as output. Okay? Very good. Now, what Einstein said, that there must exist a process like stimulated emission, and that has to be associated with a rate constant. So, the rate of stimulated emission, if we look at, so rate of stimulated emission, how can we write that? It is just like the other emission process. So, the job of an emission is to bring the atom from excited to ground state. So, by decreasing the number of population at the excited state, so I can write it is as dN2 dt, and you can separate it out from the other dN2 dt that we dealt with by writing a subscript as stimulated and spontaneous. Fine. So, here we are specifically writing that this is the rate of the stimulated emission minus dN2 dt. So, what are the things that it will depend on? It will definitely depend on the number of atoms at state 2, and in this case we are using a photon to stimulate the process. So, definitely it will depend, just like absorption process, on the density of photon having the frequency nu 1 2, all right. And we have already mentioned here this is the rate constant. So, if we put that, so minus dN2 by dt for stimulated emission is equal to the rate constant B21, again you notice it is 2 to 1 followed by N2 multiplied by rho nu H12. Okay. So, this is the rate of stimulated emission. So now I have got three processes: absorption, spontaneous emission, stimulated emission. All three processes have their own rates. So absorption process is upward movement and spontaneous and stimulated emissions are downward movement in this picture. Fine. Now if we apply the principle of detailed balance, okay, so from principle of detailed balance, I can say that the rate of upward transition is equal to the rate of total downward transition. So the total rates of both the directional movements should be same, should be the same as per the principle of detailed balance. So if I write explicitly rate of absorption, or to be specific, if I write total rate of absorption must be equal to total rate of emission. Okay. So we can use the rate expressions that we have already got. So rate of absorption is given by B12. If you recall in the last class, then we have N1 multiplied by rho h nu 12 is equal to the rate of spontaneous emission, that is A21 multiplied by N2 plus the rate of stimulated emission that we just now we got, that is B21 N2 multiplied by rho H12. So Einstein was responsible for this, this whole expression, because he brought out the fact that there must be a stimulated emission also along with the spontaneous emission. So if that is true, and if we remember what we said just few minutes back, that in 1917 Einstein could use these two level oscillators to mimic the black body radiation spectrum, and he was successful to come to the expression, same expression that Planck has got. So we should be able to use these to do the same thing, okay, and you will see that that ultimately will help us in understanding the laser process, okay. So what we need to do, if we remember in Planck's expression, so what was the Planck expression? Planck expression was this. Planck's law was for a given frequency at a particular temperature T, the spectral density was equals to 2h nu cube c square multiplied by E h nu by kt minus 1. This was Planck's work, right? So now if I try to rearrange some of these terms here to get an expression for rho 12, rho h nu 12, then how should it be? So let's transfer this term on this side first. Okay, so let's do that little explicitly so that it's easy for you to understand. So this is equal to, I am transferring this one on this side. So A21 by B12, and then again dividing by N1. So N2 by N1 plus B21 by B12 N2 by N1 into row H12. Now this term has one row, and here also we have row. So if I take this term on this side, so what will I get? I will get row H nu 1 2. If I just rearrange and simply jump a step, then I can write it as 1 minus P2 1 by P1 2 into this. And on the right side, what we have? I have A21 by P12 multiplied by N2 by N1. Fine. Now I can take this on the other side, and I can get an expression for row H nu 1 2 finally. So what I have is A21 by P12 into N2 by N1, and then 1 by this quantity. So I have 1 minus B21 divided by B12 multiplied by N2 by N1. All right. So I have got some expression for row 1 2. Sorry, row H nu 1 2. Now we have a term called N2 by N1. So what is N2 by N1? N's are the population of atoms at a particular energy state, either 1 or 2. So if you recall what Boltzmann said, that the ratio N2 by N1 is equal to e to the power minus delta E by kT, where k is a Boltzmann constant. Many occasions you will see it's written as Kb. Okay. B stands for Boltzmann. So here we are not writing that B specifically, so we are writing kT. So this we know under equilibrium, right? So when the equilibrium is established, then always I have this relation coming from Boltzmann. So if we use this instead of this N2 by N1 in this expression, I will get the expression in terms of this exponential, and here this delta E I can write further like e to the power minus H nu 1 2, right? Because the delta E here in our case actually refers to E2 minus E1, which is equals to H into nu 1 2. Okay. So use this term here, and let's see how we can solve this one. Okay. So, let me write down A21 by B12 into e to the power minus h nu 1 2 by kT divided by 1 minus B21 by B12 into e to the power minus h nu 1 2 by kT. All right. So, we have come to some expression of this sort, okay, and we will start from here in the next class to see how we can go to the same type of expression as Planck has formulated earlier, and that will help us in understanding how one can get the amplification of stimulated emission, or in other words how to get a laser. So, see you tomorrow. Thank you very much.